Alright, it's recording.
What we're going to talk about, you guys, is I want to talk about just kind of review Newton's laws.
We're not going to talk about your son anymore?
Alright, not funny. Say hi, Cody. Come up in front of the camera and say hi.
Yeah, I'll just pivot on.
Alright, so what I want to do is I want to review Newton's three laws real quickly. Because we're going to teach it just a little bit differently than you learned in pre-AP. Alright, so let's go. And one of the things also, I went to an AP teacher session a few weeks ago on a Saturday. And one of the things that this teacher said is that they do is, she said she was a grader for the College Board. And she was saying she would be reading a kid's free response problem. And all of a sudden she would see all these little things written like N2L, COE, N3L, COM. And she asked another teacher, she goes, what does this mean? And the teacher said, she goes, it meant they were using Newton's second law, conservation of energy, Newton's third law, conservation of momentum. And the idea is, what these kids will do is, to help organize their thoughts when they're doing a problem, because the thing about the AP test is they cover so many topics on one question. And like the test we just took is just projectile motion, but as you go on and on, as you cover more, everything that we learned in the past is going to be fair game. Does that make sense? Now, I didn't put any vector questions on your last test because the vector stuff is, it's hard to find good questions on vectors. But this stuff right here, or one-dimensional motion, I hardly put any, you have to apply that stuff, but as we go on and we start studying Newton's laws, all that stuff will come back to haunt you, so you have to make sure you cover all that. But what you'll do is when you take a test, if you're coming to a thing and you're going, okay, how do I start this problem? What do I do? Well, if you go and it says, if it deals with momentum, well, what principles do you know? Conservation of momentum. So that helps, and that's what she trains her students to do, is when they're taking the test. And I had never heard that before, and I've been teaching physics for years. And so I've never done that. So I just wanted to remind you, as we do that. Now this should be reviewed, so let's go over Newton's laws first. Newton's first law, N1L. What does it say?
Inertia.
Okay. Objects at rest will?
Stay at rest.
Alright, remain at rest.
Unless
And objects in motion will?
remain in motion.
Unless acted upon by an unbalanced force. Alright? Now this is what we call the law of inertia. And so the law of inertia was built on the work of Galileo. And so what Galileo did is he took a ramp. And a lot of people think, Galileo, he dropped balls off the Leaning Tower of Pisa. But what Galileo did is he rolled these balls down these ramps. And, real funny. And he noticed as the balls roll down the ramps, as time goes by, of course they accelerate, right?
Right.
So then he set up another ramp over here at the same angle and the same length. And voila, guess what happened?
Momentum carried through.
The balls rolled to the same height that they started from. Does that make sense?
It's probably more parabolic, wasn't it?
Whatever. Okay? Then he said, okay, let's take that ramp, and let me take that second ramp, and let me make it a little bit longer and change the angle. And guess what the balls did?
Same distance.
They rolled the same height. Now, there's a little bit of friction, of course, but they rolled the same height, and they rolled farther. They said, ooh, let me make that second ramp even longer. So we lowered the angle, and guess what happened?
Same height.
The balls rolled even farther. So then he said to himself, what would happen if I take this second ramp and I make it flat?
That's not a ramp.
Alright? What would happen if I take that second ramp and make it flat? It would roll forever. And so that's where Galileo got the idea that objects in motion will Stay in motion. All Newton did is said, oh, object of earth. And he added that, he gets credit. It's basically built on the work of Newton. Alright? So that's, of Galileo. So that's the idea of the law of inertia. Things want to keep on doing what they're already doing. Now, the other things you need to know about inertia, the more mass an object has, the more inertia it has, right? The brick example. More mass, the more inertia. Cody? You like this? Okay.
I liked it.
Cody liked getting a brick thrown at him. Right. So the law of inertia, the more mass, the more inertia it has. And a couple other things about Newton's first law. When we get to circular motion, we hear the term centripetal force, or centrifugal force. And centrifugal force is what kind of force? A false force. We talk about it being a real force, but it's not a real force because it's nothing more than inertia. Yes.
Is that like when I think my driving instructor, like a couple years ago, told me whenever you're going into a curve and you accelerate, that like centrifugal forces like pull you into, or are already pulling you into the curve already?
Well, the force that pushes out on you is often called centrifugal force.
Yeah, it was one of those words.
What is the difference in what I...
Okay, well, we'll get more to that when we get... Okay, here. When I was a kid, okay? Alright, and I told this to my other pre-AP kids before. But when I was a kid, we used to have a car, and it was before the days of minivans. This was my mom. My dad sat here. My mom sat here. I sat on the left side. My brother Carl sat in the middle. And my sister Kathleen sat on the right side.
And you would try to...
Alright? Now, when we would drive somewhere, my dad was a physics professor. And so when we would drive somewhere, I still remember, he said, hey, kids, you want to learn about inertia? No. I'm like, sure, Dad. So he's driving along, and he made a left-hand turn really, he'd make a little left-hand turn a little bit sharper. Well, if you think about it, if you're sitting in the car, here I am in the back seat, right here. If I'm sitting in the car right here, and he makes a left-hand turn, well, here's my brother Carl, who's 10 years younger than me. And he's a pre-cal teacher in Sweden. And my sister sat over here. So he'd make a turn, and as he turned, our bodies were going this way, weren't they? But the car's turning, and there's a force acting on our butts, which makes our butts turn. But our bodies want to do what? Keep going straight, don't they? And so what that gives us is it gives us the feeling that when we're in the car, there's some magical force that's pushing us to the outside. And people call that force centrifugal force. Centrifugal means center fleeing. And so you feel like you're being pushed to the outside, but it's not a real force. And why is it not a real force?
Because it's just inertia.
Yeah, because your body was just doing what it was doing to begin with. Does that make sense? And so what we would do is we would smush my sister into the car glass. Okay, because the force, my inertia carried me, my brother's inertia, we both carried into my sister, and the only force that would act on her was the door. And that force acted inward, and we call that centripetal force. Centripetal means center seeking. So that force acted inward on her, and then she got smushed up against the door. Well, whenever we'd make a right-hand turn, my dad would go twice as fast. He'd go faster because he knew we were smushing my sister. So he'd make a right-hand turn and he'd go even faster, and then it was my turn to get smushed. So my brother Carl, he thought he was so cool because he was avoiding getting smushed. So we would sit there. I remember my sister and I, we planned it out. We had our little hand signals, and we said, okay. And so we both, at the right time, we both put our feet up like this with him in the middle. They're both feet up on the door. This is when we had bench seats. And we just pushed like that, and we just smushed him in the middle.
Y'all have benches in your car?
What? We? It was back in the day, all right? Sorry.
What, is that the 50s?
That was Newton's law. All right, Newton's second law. And there's all kinds of other examples of first law, but, you stand on the bus, so you wear your seatbelts, because if you don't wear your seatbelts, when you brake, your body's going to keep on going forward. You're standing on the bus all of a sudden goes forward, you jerk backwards. Whiplash. Your head snaps back. Why does your head snap back? Because when you get hit from a car behind, there's a force acting on your body, but not on your head. So that part accelerates, your head wants to stand right, your head snaps back. Okay, Newton's second law. Newton's second law says Well, when an unbalanced force, I mean, if you want to watch this, I don't know if I want to put it up on YouTube. When an unbalanced force acts on an object,
Yeah, don't do that.
what happens? The object
Accelerates in
accelerates
the direction of the
At a
motion
rate.
force.
in the direction of the unbalanced, and another term for unbalanced is net force. And the idea of a net force is, if I have a force, like net, if you say, okay, I make $100, and they take out $20 for taxes, you've netted 80. And it's the idea, when you have all these forces, it's like all the force vectors. You add all these vectors up, and whatever's left over, that extra force, is what does the accelerating. Does that make sense? So, when you have an unbalanced force, the object accelerates in the direction of the unbalanced or the net force. And we write that mathematically. You learned it in pre-AP as the net force equals mass times acceleration. But in AP, we'd write it a little bit, we can still write it like that and get away with it. But when you talk about in the direction, now we say it, we write it a little bit more like this. We say, what's that symbol?
Sum.
Sigma, which is the sum of the forces in the x cause a mass to accelerate in the x. Because if you're talking about in the direction, what direction are you talking about? The sum of the forces in the y cause a mass to accelerate in the y. And so because of this idea of x's and y's, you have to come up with you have to know how to draw what we call a free body diagram. And what a free body diagram, we'll talk more about that tomorrow. A free body diagram shows all the forces acting on,
A given object.
right, on a mass. And so it helps you, a free body diagram is a tool that will help you use Newton's second law. Newton's second law is by far probably, they poll physicists, what's the most powerful law in all of physics? It's Newton's second law. Last one, Newton's third law. N3L says for every action force,
There's an equal and opposite.
oh, I can't write. For every action force, there is an equal, y'all don't pack up yet,
And opposite.
an equal and opposite reaction force. Now this idea,
Makes rockets work.
okay, you basically say the force of object A on B is equal to minus the force of object B on A. What this means is if I apply a force to something, it applies an equal and opposite force back. Does that make sense? But now here's where that's tricky. And that minus sign, this would read, the force of object A acting on B is equal to minus the force of object B acting on A. What's the minus sign mean? Opposite direction.
Yeah, adding
like-
the two together equals 0.
Like this?
Well, alright. Basically, if I push on this wall pushes back, doesn't it? I will continue this tomorrow.
Don't let
Get out
that
my
wall
face.
push you around.
Shut this stupid thing off. Bye, nerds.
You're a nerd. That's not, you're the biggest nerd here.
Oh, that's a good one. Alright. How do I shut this off?